Good afternoon, everyone. My name is Drew Burns, and I'm the Executive Director of the Slag Cement Association. I'd like to welcome you to today's webinar, The Role of Slag Cement in Creating Sulfate-Resistant Concrete. We are glad you can join us. A video recording and PDF of the presentation you are about to see will be uploaded to the SCA website, slagcement.org, following today's webinar. Attendees are in listen-only mode. You may ask questions using the dialog box in the GoToWebinar software. Our speaker will be happy to address questions at the end of this presentation. The learning objectives for today's webinar are as shown on the screen. They are also listed on the SCA website with the webinar series information. Now I'd like to introduce our speaker today. Ryan Betts is an Assistant Cement Technical Director with Argos USA. Betts provides technical support for the activities relating to the manufacturing, distribution, sales, and marketing functions of Argos USA's cement operations. He graduated with cum laude honors from Alpena Community College with an associate's degree in the Applied Sciences of Concrete Technology in 2002. Betts has more than 17 years of industry experience, including field quality assurance, laboratory management, concrete mixture design, and materials quality management. He participates in the Georgia Ready Mix Concrete Association and Georgia Chapter ACI, as well as the Alabama Concrete Industries Association and Alabama Chapter of ACI, the Mississippi Concrete Association, Portland Cement Association's Product Standards and Technology Committee, and various PCA state code groups, as well as the SCA Southeast Promotion Technical Group and the Technical and Marketing Committee with the SCA. He is active in ASTM CO1 and CO9 committees, as well as the ACI 225 and 233 committees. Now I'll hand it off to Ryan to get started with today's presentation.
Good afternoon, everybody, or good morning, depending on where you are. I'm glad that you could join us, and I'm excited to have had the privilege to be able to discuss slag cement and sulfate resistance and all of these great topics. So my goal is hopefully that you're here because you are interested in learning or you're interested in reinforcing your knowledge of sulfate attack in concrete, as well as some of the different things that can be done to manage that. So with that, Drew, you can go ahead and to the next slide. So as just a beginning and opening story, I wanted to kind of while putting this presentation together, I was recalling some of my past experiences with slag. And as Drew said, I graduated from college in 2002, went to work in the ready mix industry in Indiana. And one day I said to my boss, we were running mixes at our plants with Class C fly ash and type 1-2 cement. And I said, hey, we should use slag. And he said, why? And I said, well, because my instructor in college said that slag cement makes great concrete. And he said, well, come back with a better explanation as to why that would be good for us to do, and I'll consider it. So a year later, we were running slag at pretty much all of the plants that I was doing quality assurance for, and we were doing it very successfully. The thought had never occurred to the company I worked for that maybe adding an additional silo or freeing up a silo and using slag cement would be beneficial, but we came to find a lot of great benefit, as well as learned a lot of things about how to use slag cement and the various challenges that can come with managing three different powders in a concrete plant. So I preface that by saying that my interest in slag cement it was very early in my career, and it's been reinforced by a lot of people who have spent many more years in this industry and who have done things that are very groundbreaking as far as research and discovery of mechanisms and things like that. So the reason I tell that story is because I want you to understand that my perspective when it comes to slag cement, I'll always be that young guy who was using slag cement as part of a normal everyday production of ready mix concrete. I'm not a scientist, and as you will soon see, that my representations of various chemistry is very rudimentary. So what I'm going to try to do is I'm going to try to explain a very complicated mechanism or various mechanisms that is sulfate attack. I'm going to try to do it in a way that hopefully, even without any understanding of sulfate attack or any previous exposure to a sulfate attack, that you should be able to understand it. I also want to try to help you to identify concrete and environmental risk factors, manage the risk of sulfate attack in concrete, and then get into some of the properties of slag cement and some of the benefits of mitigating sulfate attack. And I thought it would be good to close with a few examples and specifically some exposure site type of stuff. And if you're not familiar with that, I would like to introduce you to this type of concept. So next slide. Okay, so all the time I spent on this presentation and trying to unpack the content, to rearrange the content and try to spell it out clearly, this was probably the slide I struggled the most with. I looked at various publications, including things from the PCA, from the SCA, various professors, industry people, and there is a common theme in sulfate attack, but the one that the definition that I thought was the best is this sentence you see at the top. Essentially, it explains sulfate attack as a term used to describe a series of chemical or physical reactions between sulfate ions and the components of hardened concrete, principally the cement paste, caused by exposure of concrete to sulfates and moisture. But I thought that doesn't really help you to understand what it is unless you really sort of pick it apart. And so I may get some comments about this, but I thought I'm going to try to create an equation, let's say, where I plug in the various elements that are required to create sulfate attack. And the first complication that I ran into is that sulfate attack is widely split into two main categories, one being a chemical attack and the other being a physical attack. And so I decided I was going to create two separate equations. And so basically the way that I'm approaching this is that sulfate attack, in order for a chemical sulfate attack to occur, you have to have sulfate ions, you have to have water, you have to have C3A and free lime, and they have to have accessibility to the paste. They have to be able to enter into the concrete, into the paste matrix. And that is essentially my oversimplified definition of chemical attack. So for physical sulfate attack, and if you live out in the Western US, specifically the Southwest US, you're very familiar with this. This is something that I have not been as familiar with, but have seen it when I've been in my travels out in places like Arizona and California, Nevada, in that you end up with a slightly different mechanism. So you still have to have sulfate ions, you still have to have water to dilute them into. They have to be absorbed into the concrete, and then you have to have periods of wetting and drying. And those periods of wetting and drying are very important to the process. But again, I wanted to put this comment in here. You know, is this an oversimplification of sulfate attack? Absolutely. But we could do presentation after presentation on just minute parts of this explanation. So we're going to try to sort of take a more general approach, and hopefully that is sufficient enough for us to move on with the rest of the presentation. So next slide. All right. So as I said before, sulfate attack is widely classified into two different categories. You have the chemical attack. This is some people refer to as the kind of sulfate attack you learned about in college. It's the traditional sulfate attack, and it has to do with essentially sulfates entering into concrete, whether they're already there or whether they've intruded into the concrete from external sources, and they interact with the hydration product of C3A and calcium hydroxide or free lime, and the product that is formed is etranite. And the problem with etranite is that it is expansive. It creates volume in concrete, and so over time, the concrete is growing in volume, and because of the way things we build concrete structures and various things, there's restraint to that expansion, and eventually, if it's a severe enough attack, you start to see these crazy looking cracks and things like that form. And then of course from there you have entry points to things like chloride and other nasty things that can also attack the concrete and degrade it as well. So the other kind of attack, and I've heard Doug Hooton from the University of Toronto say this is really the most underrated unless you're in an area where this happens, but it is probably the most widespread form of sulfate attack, and it's not the classic example. Some people refer to it as salt crystallization. It tends to occur in arid zones. I'd say it probably almost exclusively does, but maybe there are some other exceptions. And like I said, think about Western U.S. In Canada, places where they have high sulfate soils, they get very little rainfall, and going back in millions of years, we're part of an ancient seabed, so they were part of the floor of the ocean. So these sulfates have collected and accumulated and remain in very high concentration in soils. And then you have to have that wicking action, which from the extreme dry periods to the very temporary wet periods, you end up with concrete that's thirsty, that's lacking in moisture, and so you have this action to bring this sulfate into the concrete. And then over time, what happens is that these sulfate crystals form, and then they dissolute, and then they reform, and over time you get an expansion and contraction type of mechanism that eventually leads to cracking, and it can be a very quick, a very rapid type of formation. I remember being in Arizona at a rest stop, and this rest stop probably was about 3 years old, and I'm looking at the concrete, the sidewalks, the walkways, and there were these cracks all over it, and I thought, well, that must be what they're talking about when they're talking about physical sulfate attack. And again, I will also emphasize that the word physical is only really referring to the action of the attack, but obviously understand there is chemistry involved. There is a chemical reaction involved in physical sulfate attack, but for the purposes of sort of the classic examples, we'll refer to that as physical. Next slide. Okay, so the other component is where does the sulfate come from? And there are two places that sulfate come from. You have internal, which we're going to cover in this slide, and only a little bit in the form of trying to sort of explain DEF. And then there's the external, which is the one that is of primary concern. So when you look at internal sulfate, things come up like oversulfating cements. If you're familiar with the process of producing cement, calcium sulfate is added in the milling stage with clinker and other additives to help react or help to restrain the aluminate phases of cement from sort of taking over and creating adverse effects, things like false setting, flash setting, But when these things are incorporated in high amounts, and again, I can't find any, I really wasn't able to, a lot of documentation of this happening, but I would assume it has to be in very extreme amounts, again, with the exception of delayed etronite formation, that you can essentially sort of build in the sulfate source. So this is an attack within sulfate-rich aggregates and potential contamination. And there are some things that people may want to add to concrete, or in small amounts are perfectly fine and useful, but in large amounts or in contaminated sources, they can also cause this. So in the examples of the types of internal attacks that you'll see, and again, this isn't an exclusive list. It's the classic etronite attack, as well as delayed etronite formation. The other type of source is going to be something that comes from the environment, comes from outside of the concrete, and works its way into the concrete over time. So you have things like seawater, groundwater, wastewater. I remember very early in my career realizing that there's something unique about wastewater treatment plants, because when I look at specifications and try to design mixes to meet them, I always had these really interesting requirements that would be in wastewater. They always seem to be excessive, very low water cement ratios that produce very high strength concrete with strengths that they're only needing, 3,500 or 4,000 psi, maybe 4,500. Also, high sulfate soils. So obviously there are, outside of even just the Western U.S., there are places where there are high sulfate soils for various different reasons. And then the examples, again, we have the classic etronite attack, salt crystallization, and then thomsite, which again, I'm only going to briefly cover in this particular presentation. Next slide. All right. So thought, well, let's establish what it can look like. My favorite is thomsite. Again, this is the last time I'm going to mention it, but I will give it an honorable mention for this presentation, in that it is a phenomenon that, unless you are in some of the coldest places on Earth that are inhabited, you're probably not going to see this issue. This has to do with a cold weather, a low temperature mechanism that causes this to happen, and it is an internal. It is an external issue. The picture in the top middle is a chemical attack, and again, I know that there's probably some of you that are listening that say, well, maybe it's a combination of different things. It could be other types of things happening, but we associate this type of concrete deterioration from a chemical attack, and this is obviously from an area where you see the water levels. This is probably a seawater related issue. Physical attack, and I assure you that was not caused by poor driving. That is actually concrete that is being eaten alive from the base, and that is something that is a particular look that you can see with the physical attack. And then I made sure to put in the title of this picture on the lower left, DEF, which is delayed etronite formation / ASR, because I know that there are probably some people that will say, well, DEF and ASR happen together. You never see them not happen together. And ASR is alkali silica reaction, and you do very commonly see them together. But there is a lot of debate as to whether you have to have ASR to experience DEF. But what is agreed upon is that this is a phenomenon that only happens when concrete is initially cured at very high temperatures. It affects the sulfate phases within the cement and causes a formation of etronite that happens at a later age, when the concrete is not capable, or the paste is not capable of accommodating this increase in volume, and so you see these types of cracks. And of course, you can understand that once you have cracks in concrete, you can have all kinds of other types of deterioration problems, whether it be corrosion of steel or ASR or anything else that might cause concrete be degrading to concrete. So in the bottom right, I thought about the idea of trying to be funny during this presentation, so I put this picture up, and I was going to ask what caused this form of sulfate attack, and if you look at it, it's very obvious that these are test concrete sections, little beams or something like that. And so I was going to say that really the most destructive form of sulfate attack is science. This is an exposure site, let's say, where you're trying to cause problems with concrete and then study those problems. But again, I thought I would only mention it, and that I decided to take that out because I didn't think it would be all that funny. Next slide. Okay, so back to our equations. So sulfate ions, and understand that this is strictly, we're going to focus on
Hey, Ryan, this is Drew. I just wanted to chime in for a sec. We got a question. What does DEF stand for?
So DEF stands for delayed etronite formation, and it's a very widely and very widely debated subject, in that even some of the greatest researchers, minds in research and concrete, can't completely agree on its mechanisms. And so etronite as I explained earlier is something that is formed with sulfate, and but this is DEF is essentially just an internal issue, at least as far as I understand, and it only happens in things like mass concrete or concrete that has been intentionally cured at very high temperatures, in the ranges of 160 degrees or higher, and essentially it causes, down the road, with the introduction of, say, moisture, it causes this etronite to form and expand and degrade the concrete. So I hope that answers the question. So again, when we look at this, we're moving into the identifying risk for sulfate attack, and again, for this purpose, we're gonna focus on external sulfate sources. I think that we could probably do another talk about internal, but when it comes to sulfate ions, we're looking at where is this stuff coming from. So again, this equation, it falls apart if one thing is missing. So if you don't have sulfate ions, and I say that sulfate ions in a certain amount of appreciable quantity, then you don't have sulfate attack, just like any of the other components of this. So we're going to look at sulfate in the environment, things external sources. So next slide. So sulfate in soils and water. So we're gonna look at those, and again, soils contain moisture for the most part, and obviously water contains water. So you have sulfate, you have water. So you have the first two ingredients to causing sulfate attack. So here's a simple chart from ACI 318 building code, and what it does is it attempts to classify the severity of risk of sulfate attack. So you have 4 classes. I don't know why they didn't start with 1, but S0, I guess it just sounds like there's nothing to worry about. So S0 is exactly that. It's sulfates in the soil by percent mass that are lower than 0.1%, and in water that are less than 150 ppm, parts per million. And then as you go up through, and you see that those numbers become larger and larger until you get to S3, which has sulfate by mass. And from what I understand, those conditions can exist. It seems very high, but in certain circumstances it can, and it's the most severe risk. And then sulfates in water at 10,000, but parts per million or greater. And the one interesting thing that I like to point out, and it's something that I think gets overlooked, in that you see that seawater is classified as S1. That doesn't necessarily represent the fact that seawater is 150 to 1,500 parts per million of sulfate. It's just trying to, it's essentially lumping that in with that, non-seawater type of category. So that'll come up here in maybe the following slide. So next slide. Here it is. So this is an interesting case in that you say, well, you know, sulfates are in seawater, and they can be very high in seawater, but we know they're there. And we know that a lot of infrastructure is built around coastal areas in the Atlantic, Pacific, Caribbean, and other places of the world. And so why is it that you would only consider seawater in sulfate exposure class 1? And the plain and simple answer to that is that you also have chlorides that you're contending with, and sulfate attack is not necessarily your biggest enemy when it comes to this type of seawater concrete environment. And so the tendency by the old school ways of handling sulfate attack is as you can see over here, this is a little blip from ASTM C150, and the difference between type 1, type 2, and type 5 cement, the main difference is going to be the C3A content. And as we said earlier, that you have to have the hydration reaction component of C3A in order to have sulfate attack. So type 1 does not have a limit, and you can see ranges that go over 8%, and I've seen them in the 11, 12, even possibly 13% range. So you have a lot of this stuff. Then as you get into type 2, which is moderate sulfate resistant cement, you end up with an 8% maximum on C3A, and on type 5, you end up with a maximum 5%. Thankfully, they don't have a type 6 that requires 0%. That would be a very big challenge to all of us. And I have not had a lot of experience with type 5 cement, but I know that it is very widely used in those regions in the southern or southwest U.S. In conjunction with other things because of the severity of their sulfate attack issues. So when it comes down to it, though, the C3A isn't all that bad. When it comes to chlorides, the C3A hydration product actually binds chlorides. So you have these big structures, let's say bridges and other types of structures that are exposed to seawater. The C3A component is actually helping to sort of bind up the chlorides and sort of picking them off as they're intruding into the concrete and helping to prolong that period of time that the chlorides can get to the reinforcing steel and interact with the reinforcing steel. And obviously, once that starts to happen, it's big time trouble. So that's the explanation as to why seawater is sulfate class 1. Because what tends to happen as you get past class 1 is that you start looking at things like type 5 cements. And so what we're saying is, for this application, you need some tricalcium aluminate, the hydration product of tricalcium aluminate, because it's going to assist with a much bigger issue in the fact that corrosion is critical in structures. So next slide. All right, now that we've looked at the source, let's look at the vulnerabilities of concrete mixtures and the materials that we make concrete with to sulfate attack. So when looking at this is where you start to see in your specification all of that other stuff is done sort of on the engineering and design. They figure all that stuff out, and then they come over to the other side of these last two things and say, all right, we're going to specify something that helps to improve these things, because you can't change a lot of environments. It's just not feasible, but you still have to build concrete structures in them. So next slide. So to understand how we can quantify our risk of sulfate attack, and knowing that sulfate attack is something that's pretty much exclusively in the paste portion of our concrete, and a very high amount of this relies upon the cement itself. We'll look at the method of evaluating sulfate expansion potential or sulfate reaction potential, and that standard is ASTM C1012. Essentially, what you're going to do, and if you've produced concrete or if you've specified concrete, is that you're going to specify a certain amount of maximum expansion allowed. You're going to make, or you're going to essentially, to meet that, you're going to create mortar bar samples with various combinations of cement, blended cement, pozzolan, slag cement, microsilica, and then you're going to soak these things in a solution of sulfate, and then you're going to measure these bars over time, and over time they actually grow, and you'll see some of that data here, and they can grow very substantially, and even in a lot of cases, these mortar bars can actually crack and break up, and I like this little representation on top. It shows a poor little mortar bar that's been sitting in the sulfate solution for a while, and it's started to crack and fall apart. So, but understand too that there's essentially different specifications based on different scenarios for how much expansion is tolerable and within what time. But the minimum time is 6 months. So that's the minimum amount of time that it would take to get your final reading, and the maximum time specified is 18 months. So this is a very long-term test. So next slide. Okay, so how do you take those results and understand what you're meeting? Because sometimes, let's say on a project, an engineer says we need an exposure class S2. You can essentially utilize this chart that I believe is in the latest version of 318. It's the updated version. This is probably, a lot of you probably haven't seen it. I have not actually seen it in the standard because I don't have access to it. but anyway, so you can see how there's a few different mechanisms here. One is the severity of sulfate exposure, the classes. The other thing that is moving the requirements is water cement ratio, and as we'll demonstrate later, water cement ratio is paramount in the importance of reducing and mitigating sulfate attack. And then you have your cementing materials, and then you also have your C1012 tests, and you can see as you move through the sulfate exposure classes, you're moving from no requirements to type 5 cement and low water cement ratios. So class S3, if you have a 0.40 water cement ratio, you've got to use type 5 cement, or you have to use a type HS, which you can achieve through either a blended cement, say a slag blended cement, a pozzolan blended cement, or a combination, or you can take your cement, your type 2 cement, your type 5 cement, and blend it with things like fly ash and slag cements and other things, which is very commonly done. But when it comes down to it, in order for it to meet your combination of cementitious materials to meet the requirement, they have to meet these maximum expansion numbers within the time frame. So that's the big important thing to understand. All right, next slide. Okay, so managing the risk of sulfate attack. So here are a few of common themes of things that are approached when it comes to managing sulfate attack. This is obviously on the premise that you have some sort of a sulfate exposure level that's greater than 0. And here are some of the things that are done. Reducing the cement C3A content. We said that's a foundational part of sulfate attack. You reduce the C3A, you reduce the amount of hydration product that is highly vulnerable to attack by sulfate, and these are accomplished through things like type 2 cement, type 5 cement use, or moderate sulfate and high sulfate resistant cements, which are a blended spec, which are a blended cement that meets a performance spec. Reduction of paste permeability, and again, I say this is probably one of the things that everybody sort of understands, and it translates to a lot of different problems in concrete. But the more permeable the paste is, i.e. the more water to cement that was used, the higher the water cement ratio, the more opportunity there are for things that shouldn't be in concrete, that you don't want to get into hardened concrete to get there. So managing water cement ratios, specifying proper water cement ratios is very critical. And then the use of suitable replacements of SCMs. So it's not just suitable amounts, it's also suitable SCMs. And as you'll see, there are not all supplementary cementitious materials are created equally. And these things include things like slag cement and F-ash and silica fume, and can even include metakaolin or calcine clays and other types of natural pozzolans. And the effect that they have is really sort of it reaches all of these the other two. So one is that you get a dilution effect. So if you take out a pound of cement and you replace it with a pound of SCM, as long as that SCM doesn't contain C3A, then you're diluting or reducing the amount of C3A, which is very important for this whole process. You're also reducing paste permeability because these SCMs are later reacting components. They utilize free lime, which is another component we said that is used in sulfate attack by sulfates to attack concrete. They utilize the free lime, and then they have a delayed hydration reaction, and then they further densify paste, so they reduce the permeability. So SCMs are a very good thing when they're available and when they are of proper quality. So next slide. So here's an example of a situation where adding SCMs is actually detrimental. In certain areas of the country, there are a lot of Class C fly ashes. And I don't want to say Class C fly ash is bad, but I want to say that it doesn't necessarily solve durability problems, and specifically with regard to sulfate attack. There is a sort of a breaking point, an established breaking point, and it all has to do with the calcium oxide. So what happens is as you move from Class F fly ashes, which can have calcium oxide contents of 2 and 3% and higher, you move into that 18% threshold. You're getting into Class C fly ashes, and they have less pozzolanic reaction and more cementitious or cementing reaction. So Class C fly ash will actually react. Class F fly ash, you can add water to it, it does nothing. It needs certain things to activate it, like free lime and alkali, soluble alkali and things of that nature. So again, that's why that 10-12 test is important, especially in an environment where things like Class F fly ash and even quality sources of Class F fly ash are becoming very irregular. The supply is. If you have a project where sulfate resistance is important, don't swap Class F ash for Class C ash. It's a good opportunity maybe for you to go back and say maybe we ought to look at the Class C fly ash, because you can use it as long as you demonstrate that it is suitable for mitigating sulfate attack. So yeah, this is a two-year soak in sodium sulfate, and it's amazing how destructive the sodium sulfate was to that. And I would say that may be as bad and potentially could have been even worse than a version of that mortar bar made only with the cement and without the fly ash. So sometimes Class C fly ashes can actually increase problems of durability, not just not help. So next slide. Okay, we touched on water cement ratio. This is a fairly drastic contrast when it comes to what's the effect of water cement ratio on sulfate attack. But I promise you that even with tighter bands, say 0.4, 0.45, 0.5, you can see very substantial differences in the effect of sulfate attack based on water cement ratio. And again, that plays into that permeability of concrete. So here are field exposure concrete samples that are made with type 5 cement. One, they used a 0.38, and one they used a 0.65. And essentially everything else is the same. And so this is actually in Sacramento. And it was an exposure study, I believe, done by PCA years ago. This is 12 years of exposure, and you can tell there is a substantial difference in the integrity of these concretes based on only the water cement ratio being different. So it's a big important factor. Next slide. Okay, I said we were going to do it, so let's do it. We have delayed etronite formation, and again, I don't want to scare anybody off. I have been producing a producer of concrete for many years, as well as somebody who services and supplies cement to concrete producers, and I have yet to have one of these problems come up, or if it has, it has not been identified as DEF. But again, like I was saying earlier, you delayed etronite formation is a late formation of etronite, and it essentially happens when you have initial curing temperatures in excess of 158 degrees. Now that's for an OPC, that's for an ordinary Portland cement type mix. And this etronite formation, as you can see from this picture, it looks like my arrows kind of went a little off, but that green arrow is pointing towards a little dark band that is sort of at the edge of the aggregate. And what happens is that after the concrete is hardened, this etronite forms and it starts pushing between an aggregate particle and paste particle, and you can see the white lines are sort of generally pointing towards these cracks that have evolved. And so this is the etronite here. And so if you look above that, you see this crack pattern. Well, this is stress that's built up because you have this etronite forming in between your hardened paste and your aggregate particle. And if you look back over to the right, center right, you can see the white bands that are labeled CH. That's calcium hydroxide. So that's the stuff that you want. But again, it's the reason that etronite is so nefarious is the fact that it carries a lot of volume. It converts elements of low volume into very high volume elements. Again, there have been a few instances of it, and if you've ever listened to Mike Thomas from the University of New Brunswick speak, I think he's a very, very knowledgeable person in this and has investigated a lot of things. He would tell you that typically you see both delayed etronite formation and alkali silica reaction. He has yet to see in all of his travels and all of the investigations that it happens, although there are others who say they can make delayed etronite formation happen without ASR. So, but typically they go hand in hand. So, next slide. Okay, so we're into the segment specifically focusing on slag cement, and if you've been through an SCA presentation, these next couple of slides will probably look pretty familiar to you. But just as a brief sort of overview, if you're not familiar with slag, slag is a product that comes from producing iron, and not just iron, but iron that is produced by blast furnace, not electric arc furnace. And what you have is a molten material and a fluxing agent that is used to draw out the impurities. And as you can see from the picture on the lower right, that's labeled slag. That's what slag looks like as it's resting on top of this molten steel, molten iron. The way that it becomes a cement product or becomes a cement is that it has to be quenched. It has to be cooled very rapidly so that it can form glass. And then this, of course, is ground down into a fine powder, and you can sort of see a color contrast difference between, say, Portland cement on the right of the slag and microsilica on the left, and I think fly ash, metakaolin, and then I don't know what the other one, maybe another fly ash, maybe they're all fly ash, I don't know, but it's a very white in color type of finished product once it's ground. So next slide. And interestingly, this handful of stuff this person's holding in this picture is what slag cement looks like before it's ground. So it's not white before it's ground, but after it's ground, it becomes white. And if you look at a microscopic view of slag cement, you can see that it's angular. You've got some different particle sizes, and typically it's going to be something in the range of slightly finer than Portland cement. And if you look at this mill to the right, the grinding facility, that's a pretty standard mill. If you've been around a cement plant that has a ball mill, roller ball mill, it's the same exact type of equipment. So it's ground on the same type of equipment that you would grind cement. Next slide. Whoa, that didn't come out right. Okay. It's okay, Drew. So we're gonna have to use our imaginations here a little bit, but
sorry, Ryan, I can pull up the original slide for this too. Hang on just a second.
No worries. So what this is, I think it's a wonderful illustration if it was fully colored in, but apparently didn't make it in the translation. But you can see that light area that says aggregate. Imagine there's an aggregate particle there, and you're looking at two different systems. A system that the paste is comprised of only Portland cement, or at least the powder component of it is only Portland cement. And then you see a Portland cement and slag. And what you see is these gray particles represent cement particles. The yellow coatings around them represent the hydration product, the reaction product that happens through the hydration process, which is called calcium silicate hydrate, CSH. Then what you end up with is obviously these microscopic voids, and in this case they're very large, but I promise you there was more dense. This isn't as dramatic as it seems, but and when you look at the difference between the slag cement matrix system and the Portland cement system, what you notice is that there are far less voids because the slag cement has essentially, there we go, perfect. So this is a little better representation. So now you can kind of see what I'm talking about, in that the idea is that obviously this is an over dramatized version of what happens. This is not accurate to scale or anything like that, but the idea is that that calcium silicate hydrate that we talked about, that is essentially the free lime. The lime is not used in the cement hydration process, is actually beneficiated by slag cement, and then it helps it to create some additional hydration product, and so what you end up with is a less porous pore structure of your paste. So again, we were talking about why is that important? It's important because preventing things from entering into concrete is a big part of preventing destructive mechanisms that cause concrete to fall apart. So that's all I have on that slide, Drew. Perfect. Okay, so permeability, and if you've ever used slag cement, or if you've ever been required to meet low permeability, I recommend that you consider slag where it's available, because it's by far one of the best products that can be used. And I will say that maybe outside of microsilica, but if you've ever actually tried to produce that via ready mix concrete, you would understand the challenges. It's not a very friendly product to work with. It's not a friendly product to place. There's difficulties in pumping and placing and consolidating and things like that. But slag cement, considering that it does not have a drastic impact on the plastic properties of concrete, is a fantastic way to reduce permeability. And it's the big thing about it is that, and there has been a sort of a mindset change in the specifying community, that the rapid chloride permeability test, which you're seeing is sort of a setup of the apparatus and the cells. The curing age on the concrete would be 28 days, but inevitably you miss some of the benefit of slag cement, especially slag cement at replacement levels of 40, 50, 60%. And it's probably more realistic anyway over a period of time that a concrete structure will be able to sort of continue to cure, as long as it's provided with moist environment and reasonable temperatures. It should cure out past 28 days worth of effective curing. So, but what you're looking at is essentially this is a single cell for a chloride permeability rapid method unit, and you have NaOH in one and sodium chloride in the other cells, those plastic cells the guy's got his thumb on, and strapped in between this is a section of concrete. Typically it's a 4x8 cylinder. You cut, I think, a 2-inch section, you strap that thing in, you fill the solution up, and then you have a positive and negative lead to it, and you're essentially forcing current through it and then measuring the amount of charge that passed. So it's represented by coulombs. And I hope I'm not confusing this with other types of permeability, because there are other methods of permeability, but it's still a good indicator of how permeable concrete is, even if its main intent is to understand how permeable is concrete for chlorides. So next slide. Okay, now to the expansion chart. So we talked about the C1012 tests. We understand that these are mortar bars and they're measured over time, and usually that time is 6, 12, or 18 months. There are a lot of studies that are done long term that are measuring these things out years if they're surviving. But essentially what you're looking at is a scenario where you have an ordinary Portland cement, and it's represented by that, I don't know, call it brownish, greenish, whatever color line. And then you have two scenarios of slag cement replacement. You can see the specification limit. So you have in this case, they're putting this against a 1-year limit, and a 1.5-year limit, or 180 day. And so, or I'm sorry, half-year limit, my fault. But you can see that even the introduction of 25% slag cement, you get a substantial reduction in the expansion due to sulfate, and that's because you have less of the C3A component, you have lower permeability, and you have other things that are driving that expansion rate down. So Next slide. Now this is a slide that the first time I saw it, this is a chart, I'm sorry, that was mind blowing to me. So we talked about delayed etronite formation and how critical of a issue it can be, albeit rare. When it happens, it's destructive. And this is something done at the University of Toronto, that they use type 3 cement. And type 3 cement is known for being fine ground. A lot of times it can have high C3A. I don't know about this particular cement. And it creates a lot of heat of hydration very early. We grind it fine. We select chemistry to solicit very early reaction, because in some environments like precast concrete and others, post-tension construction, time is very critical. And so you look at these samples that were created, with these mortar bar samples that were created. They essentially made these samples, they cured them at 203 degrees, and remember we said earlier 158 degrees is sort of considered to be the critical point for say an OPC mix, and then 185 degrees is for a mix with SCMs. And they did 3 different levels of slag cement, and obviously because there was so much expansion in this type 3, this OPC type 3 mix, and almost none in the 25, 35, and 50% replacement for slag cement, that it's very dramatized. But the reality of it is that anything over 0.1% is considered to be deleterious, and you have this OPC mixture over 2.5%, somewhere between 2.5% and 3%. And then you look at the varying replacements of slag, and you can't even hardly see them. It is obvious. It's very obvious to me that if you need to cure concrete at high temperatures to solicit early strength gain, that even a small amount of slag cement can act as an insurance policy against this rare but detrimental form of sulfate attack in DEF. So I think this is a wonderful illustration that shows how beneficial that something like slag cement can be, even at fairly reasonably low replacement levels. So next slide. So here's another, here's something out of ACI 233, and it's essentially showing kind of the same thing we saw earlier. You look at where the red X's are. These are sulfate expansion bars with no slag cement, and then you look at varying replacement levels, and you see how you are decreasing the expansion over time. So that's pretty much all I wanted to show on that. Next slide. And here's another good example. And people say, well, I can't find type 5 cement. It's hard to come by in some places, especially if you're east of the Mississippi. There are producers that supply it. It's in limited quantity typically, and it's usually someplace that you don't want to go to get it because of haul rates and things of that nature. So ACI 233, which I should reference, is part of. It's the guide for use of slag cement and concrete and mortars, but they say here's their way to address the problem. If you want something equivalent to type 2 cement and you have a type 1 cement, use 25 to 50% slag. If you want something equivalent to type 5 cement and you're using type 1 cement, 35 to 65. These are fairly good rules of thumb and very well supported. And then for lower permeability, you can see that range just opens up from 25 to 65, and I would even say 15% is going to give you lower permeability. Any percent more than 0 when it comes to an OPC mix, you're going to get the benefit of lower permeability. But in these ranges, you're going to get the best effect of low permeability. So next slide. So we're talking about field exposure sites. So I'm going to kind of glaze over this, but essentially this is an experiment that was done. There were multiple scenarios. They were looking at 1L cement and type 5 cement, the 1L cement having 40 and 50% slag, which is kind of like fairly similar to what I showed you in the previous slide. That their question is, can we get good sulfate resistance? And so they made these samples, they bury them in the ground, and they sort of manipulate the sulfate levels, and then they sort of pull these things out and visually inspect them. So next slide. So what I wanted to reinforce is that that essentially what you see is what they observed from this after 33 months was minor damage for all of the samples except for one. So the two type 5 samples had minor damage in the sulfate environment. The 1L with 40% slag had minor damage, so it was very comparable. And then the 1L cement, which is, if I guess I should probably explain, this is a blended cement that is limestone, and the 10.5 represents the amount of non-calcined limestone. So it's an addition to the finish mill. So but at 50% replacement of slag, it actually performed better than within this 33-month time period than the type 5 cement. So that's a very impressive example. So next slide. I think this is my last one. I know we're running a minute over, but if 33 months isn't enough for you, now this isn't a field exposure, but I thought this was a great way to end this discussion, in that what can slag cement do over the long term for durability? You're looking at, essentially, starting at the bottom, you're looking at a MS cement. So this is a moderate sulfate cement, so the equivalent of a type 2 at a 0.5 water cement ratio. You're looking at an HS, which is the equivalent of a type 5. And then you're looking at a GU cement, and I didn't have the, I know I meant to incorporate the notes, but you're talking about a GU cement that has something like far above 8% tricalcium aluminum. I believe for this one it was like 11.5%. So it's very high by typical standards for general use cement. But what you see is that with 65% slag cement at a 0.45 water cement ratio, after 38 years in 2 different sulfate solutions, it's by far the best looking concrete. And so if you want to know, does slag cement help mitigate sulfate, not just in the short term, but over time, I think this is a fantastic example of the potential that slag cement has for creating long-term durable concrete. So that is the conclusion of my presentation. So I'll open it up to any questions anybody may have.
All right, we do have a few questions as I go through them. Here's one really quick. When slag has high aluminum content, plus or minus 15%, how does that affect the sulfate resistance of concrete? And how does the gypsum help in mitigating the expansion?
Wow, that's a very well-informed question. That's a very important topic, and it's one that if I would have had more time within this, I would have liked to cover it in a segment. But since you've asked, let's try to address that. So there is definitely research out there that shows that there is a relationship between the alumina content of slag cement and the sulfate resistance that it can provide. And there have been various different studies done, and some with lower 5, 6, 7, 8% alumina, some at 11, some even up in the, there's a lot of stuff being done up in the 15 to 18% range. But the long story short is, without some sort of a process addition and grinding, that is like something like gypsum or limestone, a limestone addition, you will not see the same benefit of the reduction in sulfate expansion. And obviously, like we said, sulfate expansion is sulfate's target aluminates. And so putting that gypsum in there, which is a source of sulfate, causes that reaction to happen, causes that positive reaction to happen. And so there is a lot of data out there that shows, I think 233R, ACI 233R covers that as well. But and I know that specifically this question has come about in places like Florida, where in some other coastal places where we're importing slag granules or finished slag product. And that slag can be from places like Southeast Asia. And in Southeast Asia, they just the slag products, the slag granules, the slag cements that are produced from those plants tend to have high alumina. In more domestic sources, it tends to be fairly low, but there are other places where you see these varying amounts. But I think that there is enough research and verification done that if you look at the comparative data, that you're going to find that this aluminate issue in slag cement can be easily overcome by optimizing, adding the right amount of gypsum and/or adding the right amount of limestone to the process, to the finished product. So, fantastic question.
And just a note on this, we're getting a lot of questions of, is this being recorded and will it be available? The answer is yes. There's a webinar and video section on the SCA website that this will be uploaded to, as well as all our other webinars as well. I think we already touched on this, Ryan, but is there any C3A in slag, and how does higher C3A affect sulfate resistance? But I think you may have covered that already.
So slag doesn't necessarily have C3A, but that doesn't mean it can't be the aluminates can potentially combine with other things and create something like C3A. And just as a background, C3A is not a perfect chemistry. We try to oversimplify cement chemistry, but the C3A it varies greatly in its form. It's just a general term used to describe essentially calcium and aluminate products or compounds. So the compounds can vary by quite a bit, but that's a good question. Now, there are some Class C fly ashes that potentially can have some C3A, but again, it's not necessarily C3A. In those cases, it's the alumina that is obviously what needs to be focused on.
Another question for you. Please give a short brief on thaumasite.
Well, again, I wasn't sure of my audience, but my understanding is that if you're in sort of the northern reaches of Canada, Scandinavia, places where you have very sustained cold periods without, say, temperatures getting much above freezing, that essentially you end up with this phenomenon that is thaumasite. And thaumasite it's almost like a carbonation attack. It's actually slowly breaking reversing the process of calcium silicate hydrate or the aluminate, the calcium aluminate component of it. And so you end up with something that you can sit there and rub dust off of the exterior of it. It can turn to mush. I mean, I don't know if you've ever seen examples of concrete reverting back to just about like plastic concrete, but maybe that's not a fair analogy. But with moisture, it becomes sort of amorphous. It's not rigid. It's not hard anymore. It's very much like mush. So as far as the specific mechanisms, I'd have to go back and do my homework. I'm located in the Southeast U.S., so thaumasite is in no way, shape, or form a huge concern in the Southeast U.S., but I can understand in some places it may be. But as far as my understanding and the research that's been done by the University of Toronto, the University of New Brunswick, is that even in Canada, you're still looking at these things occurring, that it places far north of the main population centers, very extreme north. So
And we do have different regional groups. As Ryan suggested, he's in more of the Southeast region. And if you have other questions that maybe pertain more to more colder weather climates, we can issue those questions to our regional groups in the north too, if you want to shoot them to me after the presentation. One last question, and I'll address this too really quickly. Is there an abundant supply of slag in the United States? Kind of a loaded question. Obviously, with any material, things depend on region. One resource that we do have on the SCA's website is a state-by-state slag cement locator that allows you to see the producers that are in that state or that region. And then you can go from there and discuss with them what kind of supply they have there. And I don't know if, Ryan, you wanted to add to that at all, but that was the last question we had.
Well, I know why the question's being asked, because of concern about fly ash. And I will say that the one positive thing about slag is that while the domestic supply of granules is fairly limited, that the global supply is pretty ample, and so that doesn't help if you're in, I don't know, Nebraska, but it does certainly help in a lot of different places like the West Coast and the Gulf Coast, the Mid-Atlantic, Northeast Florida, and so these granules can come from various different places, like I said, Southeast Asia, like places like Japan and Korea. They can come from Turkey, and the good thing about the steel industry is that it tracks pretty well with demand in the concrete industry, as opposed to fly ash, which is driven by demand for power consumption. It's not always available when you really want it, and of course we know the initiatives that are going on with green energy and things of that nature, and so new capacity is not coming online with coal plants that are producing fly ash. So to me, it matches a lot. It can match a lot better with the demand for SCMs in concrete.
One more question we got. Can we do curing with seawater?
Sure. I mean, concrete's cured all the time in seawater. The obviously the big concern is the inundation of chlorides and sulfates. And I assume this is a question as far as if we were you're not planning to implement seawater curing in your laboratory, but in the real world. But the biggest vulnerability is that fresh or early age concrete, especially with SCMs, is relatively porous, because you have to wait for that sort of that secondary reaction to happen, with the SCMs, fly ashes and slags. But over time, it will become much lower permeable. And yeah, obviously there's an issue if you're asking about, would you mix concrete with seawater? I know some people are trying to do that, and maybe they're making some breakthroughs, but I can't recommend it for myself or for you or for any customers at this point. It'd be great if we could figure out how to beneficiate it, but again, like I said, there's concrete that is placed in the oceans all the time, in places like Florida, Louisiana, the West Coast. So yeah, it's very possible to where seawater could be sort of the curing, because it happens.
Well, thank you, Ryan, and thank you for everybody attending today. Just another reminder, the recording will be available on our website. And please visit the SCA website at slagcement.org for any more information that you might want to find on this topic. There's a bunch of technical fact sheets on the website. The slag cement PCR, EPD, and LCA calculator is also there, and these are all free resources to download. Thank you again for attending today's webinar. If you haven't done so already, check out the other great webinars scheduled throughout the summer. Thanks everyone, and have a great day.